Okay, so this will be the follow-up session from the stats revision session I did yesterday. Depending when you've seen it, obviously. But this will be the mechanics part of it. So this is again from June 2022. Um, and I've already did the stats 2022. So I guess let's jump into it. I guess. Okay, question one. At time t seconds, a particle p has velocity v, where v is this expression here. Find the speed of p at time t is 2. Okay. When you have expressions like this, when it's like a variable function, like it's functions of t, clearly, right? There's no like constants or anything like that. And clearly we're not dealing with constant acceleration here. So we cannot use that here. Okay, that's the key thing to realise. And so really quite limited. The only thing you can do is realise that displacement r or s, depending on what you call it, that differentiates to with respect to t, the velocity, and that will again differentiate to acceleration, and then we can go backwards and integrate with respect to t, and then integrate with respect to t. Okay, that you need to learn how that works and how you can use calculus, differentiation, integration to convert between acceleration, velocity, and displacement. But it's asking for the speed. So actually, first of all, the speed. That's just the magnitude of the velocity. So you should know as well that the magnitude of the velocity. So you do the Pythagoras. That will be speed, and likewise the Pythagoras of or the magnitude of the displacement vector will give you distance. Okay, distance and speed are not vectors. They do not have directions like this. All they have is a size. They have a single number, and so that will be the displacement. Okay, so speed at time t is 2, and let's substitute t is 2 into v. So v then would be 3 of 2 squared. I'm going to do it as a column. I don't like this I and j, so you can just do it like a vector like this as a column. So 3 squared I, that's the top part, and then minus 6, 2 of a half j, which would be the bottom part. Okay, and so then I guess you put that to the calculator or whatever. 302 squared would be 12. And minus 6 of 2 to the half. Oh, that would be, well, it would be a decimal, but that's because 2 to the half is root 2. So that's just going to be minus 6 root 2, okay? The calculator will give a decimal here, but you do need to realise that any bit to a half will be a square root, right? But that'd be fine because then if we're doing the modulus then, so mod of v of when t is 2 for this vector, we're squaring it anyway, so that I get rid of the square root. So then the mod v then is going to be root 12 squared. So the squares of the components plus minus 6 root 2 all squared. And so that will be oh, that gives you 6 root 6. Cool. Okay, and then part B, find an expression in terms of t, I, and j for the acceleration. There we go. So now, if we're going to go from velocity to acceleration, we need to differentiate the velocity vector, right? And so let's go ahead with that. So firstly, v. Let's restate v in terms of t. So v is, and again, I don't like this notation of I and j, so I'm going to say 3t squared and minus 6t to the half, was it? Let me check. Yes. Okay, so then we're going to differentiate. So A. When you differentiate, right, it's kind of what you expect. You just differentiate each part on its own. So 3t squared will differentiate to 6t, so that would be the top part. And then minus 6t to the half. Obviously, half of minus 6 is minus 3. T to the minus a half, okay? Um, and yeah, that's the vector. But then it says to give it in terms of I and j, so then we need to convert it back to this sort of form here. So then that will be 6t, lots of I, underline it to show it's a vector, minus 3t to the minus a half j, and there's our answer. Cool, so pretty typical that is, to do something like that with the vectors, use differentiation and whatnot. Then it says at time t is for the position vector of p, so now we're dealing with distance displacement, is I minus 4j. Find the position vector at p at time t is 1. Okay, so what we need to do is integrate now to go from v over here to r, which is your displacement. And what r says is, particularly with variable acceleration, r gives you the position vector at that moment of time at t, which is what we want in this case. So we're going to have to integrate. So again, v again is 3t squared. You don't have to write this, that's just for my sake. Because I don't want to keep scrolling. So that's v. Then we're going to want to do r. And that's the displacement vector. Obviously, basically the position where the particle is at time t. And then we integrate again. We integrate both parts. So 3t squared will integrate to t cubed. So add 1 to the power divide. So 3 over 3 is 1 t cubed. Then minus 6t to the half. Well, a half add 1 is 3 over 2. Then I'm going to do minus 6 divided by 3 over 2. Obviously, you should recognise that's the time number 2 over 3. But then it's going to be 3 over 2. And so that simplifies to t cubed and minus 4. T to the 3 over 2. Okay, but also, when we're integrating, we have a plus c, don't we? So that means when we integrate the top part, we're going to have a plus c. And then when we integrate the bottom part, we're going to have another constant, say d. Okay. And so that'll be plus c and plus d. However, I don't like doing it there. What I instead say is, well, if we add in a different number to both top and bottom, we're effectively just adding another vector, aren't we? So I could just call another vector the c vector, right? For the plus c in vector form. That's your like constant of integration, right? As a vector. But now we need to find the c. So we need a condition, right? And we're given a condition. At time t is 4, we're given a position vector of I minus 4. So let's substitute t is 4 in. So then r, which equals then 4 cubed minus 4, 3 over 2, plus c. And actually that equals, what did it say? It was the position vector was I minus 4, I minus 4j. So the I component is 1, and the j component is minus 4. So now we have an equation. Okay, let's simplify this a bit. So 4 cubed is going to be 64, and minus 4 to the 4, 3 over 2, is going to get us minus 32. Plus this vector c is 1 to minus 4. Now we need to find c, but we can rearrange this, can't we? Then we can say that c is going to be 1 minus 4 minus the vector 64 minus 32. And it works in the way you expect, obviously. So you take away the top part, so 1 minus 64 is minus 63. Minus 4 minus 32. Well, minus 4 add 32 is going to be 28. So that's your C vector. Okay. So that means okay. So now found R, like the displacement vector in terms of T. But he's asking to find the position vector at T 1. So now we need to substitute T 1 back into R. Um, to get R is equal to so R was T cubed, so it's going to be 1 cubed. Minus 4 1 3 over 2, and then we got this plus C vector, haven't we? So it's going to be plus minus 63 28. So that's going to be um, yes. So that's going to be, well, 1 minus 63 is going to be minus 62. Minus 4 to the, well, that's just going to be minus 4, isn't it? And then add 28. 28 minus 4 will be 24. And that would be your position vector at time t is 1. Cool. And that's what R does, by the way. With variable acceleration, particularly when you're integrating or whatnot, the R specifically gives you the position vector at time t is 1. So I might potentially ask you instead, perhaps say we had these two vectors for t's 1, t's 4, which we worked out, right? You can work both of those out, just integrating and substituting 1 and 4 in to get the two position vectors here and here. But then suppose it asks for the distance travelled in those 3 seconds, right? What you then need to do is you need to find this vector here, which is kind of like doing like OB, AB is like OB minus OA, right? And so that will come from, say if you have an origin point here that connects obviously these two vectors together to give their position vector. If you want to find this, the vector of this line, and then the idea is once you find the vector, take the modulus, that'll be the distance, right, between the points. Instead, for you want to go here to here, you can instead go here and then here. Well, this is minus the first, the position vector, the first point, right? And then add the position vector, the last point, and that's how you'd work that out. So it'd be like R4 for T is 4 minus R1 with T is 1. Okay, that would be the vector between the 2 points. That gives you the displacement vector, but then the distance would be the modulus. I don't know. I think I'll cover a question like that if I do another paper. But for R, in this sort of idea with variable acceleration, R will always just be the position vector. I say that because when you then use Suvat, it's not no longer the position vector. We'll look at a question maybe about that. But anyway, let's move on. Okay, question 2. We are given a rough plane is inclined to the horizontal angle alpha. A small block B of mass 5 is held in equilibrium by a horizontal force of x, which is shown here. The block B is model of the particle. The magnitude is 68%. Okay, so so these questions are always the same, right? But you just need to label all the forces. Okay. So um, we all knew are given a horizontal force of x, right? Now we need firstly the weight, right? Now weight is mass times g, where g is obviously the gravity, which is like 9.8. But that's going to be acting straight down here, mg. Um, no, 5g, because we know what m is, sorry, 5g. But the issue is when you're resolving your forces, it's particularly with this type of question, you're going to be resolving perpendicular to the plane and parallel to the plane. That's perpendicular, that'd be parallel. This is just straight down. This is just a downwards direction. That's not parallel or nor perpendicular to the plane. So what we need to do is create two components that are perpendicular and parallel like this. So this is going down, then the perpendicular component will be going there, and then the parallel component will be going there. And then obviously that'd be a 90-degree angle. So that's 5G. So what you need to realize is this angle is going to be alpha. Okay. Um, that'll be because you can construct a sort of Z angle like this. And you should remember for G to C be two parallel lines that this forms an alternate angle, and so they would be equal. Okay. I'm just trying to see. I'm trying to. I think you're fairly used to that. That's the same thing all the time with the maths. I'm not going to go into that maybe at the moment. But then that would mean this component here is going to be now it's not facing the angle alpha, so it's going to be mg or 5g cos alpha, and then this part down here is going to be 5g sine alpha. Okay, that's going this way. And that's facing the angle, and that's how you can tell which one's sine and which one's cos. Sine, remember, opposite, so it's going to be facing the angle, and then cos is also the other one. Okay, so I'm going to get rid of this 5G now. It's a bit messy. Just keep these two parts. I'm not interested in that. Okay, so that's the maths dealt with. Now we're told it's a rough plane. So that means there's friction. Now, where would friction be? Actually, it doesn't really matter where you pull it because if you do it in one way, you just get the negative. So you just flip the sign. But I guess before you apply the angle X, right? Obviously there'd be weight um, acting down, pulling the block down the slope. It would move down. So then there'd be friction that side to oppose the motion, right? However, then this force X is pushing it up the plane, and now it's at rest. So now, really, the particle's being pushed up. So then the friction is going to act down here. Okay. No, actually, I'm going to leave. I'm not going to draw it down here. I'm going to draw it on this side. So I'm going to say F is here. Um, okay. So friction will be pushing it up because of this horizontal force. But if you were unsure if it was meant to be that side or that side to the left or right, it won't matter. In fact, I might try to do both ways to see it doesn't matter. But it should be that way. And then what other force? Well, we've got a reaction force, haven't we? Because it's on the slope, it's on the surface. It's going to have a reaction force of R, but actually the total R is 68.6. Cool. And then the last thing is dealing with this X. And again, the X is just a straight one, right? It's not parallel or perpendicular. So what we need to do is then create a perpendicular component and a parallel component there, okay, to the plane. That's probably the best way to do it. And actually then this angle would be alpha here. Now, why is that? Okay, let's illustrate what's going on here. So we have the plane here, and then we have this horizontal component here. So actually, you can see these two lines are parallel. So that's x, and obviously that's just the slope. Now, this angle is alpha, and particularly we create this triangle here, right? That's a z angle, so this is going to be alpha, right? Because we've got this situation going on. That's alpha, so that's alpha, okay? So hopefully you can see, I probably should zoom in a little bit, that because of the alternate angles, that particular angle there is going to be alpha. Let me zoom in because it's a little bit tiny. Uh, Here we go. There, so that's the force diagram. It's a bit messy. Um, so hopefully you can see that this angle here that I created is alpha between the block and the normal force, right? The x here. So actually, also, if you want to work out which way the perpendicular and the parallel force is going, well, this the x force is going this way, so we need to correct, and we start from here, so we need to go down here and then up there, okay, to then get the same force. Okay, and then therefore so that's going to be facing the angle. So this is going to be x sine alpha, and this is going to be x cos alpha. Okay, and so we resolved it in terms of parallel perpendicular. Okay, I think that's the tricky thing here is realizing that this is alpha as well. So again, to reiterate one last time, so we have the plane there, and then it's going up. And that's x, right? So our angle here we're interested in, and but we know this is alpha, so that's also alpha because it's a z angle. Okay, it's alternate angle from G to C. Okay, and if you aren't sure, well, now it's a recap that if you have an angle that between two parallel lines here and here, and then formed like this, they're equal because they're alternate. Okay, cool. So we've labelled it now. Although a little bit messy, but I don't know. Hopefully, you can work with it. Okay, we've labelled it all now. And so once you label it, I think that's the hardest part, right? Is labeling it because now all uh. So then, if we're resolving, it's also a good idea. Probably just literally put everything you know, which means resolve in. It'll take moments if necessary, but I'm not taking moments here. Um, we're just going to be resolving. And so let's resolve and create some equations. Once we listed, all of the questions you have to use it anyway. At some point, you're going to need to resolve it anyway. So let's just do it now at the start before we do anything else. So let's resolve. So we're going to go perpendicular to the plane. I'm going to note it like this. Okay, so I'm going to say resolve perpendicular. And so what are the perpendicular components if we have a look? So we want it that's going this way, and then the forces are going the opposite way. So what's going this way first of all? Well, x cos alpha here is going up the plane, and we also is there anything else we have? No. So then what's going down the plane perpendicular? It's f first of all here, but also we have this weight component 5g sine alpha. So then if we resolve it, well, then these are equal because it's an equilibrium. So these are going to be equal. So x cos alpha is going to be equal to f add 5g sine theta, alpha, sorry. Uh, and then we're going to do the other one. So we're going to do, oh no, that's parallel side. Now we're going to do perpendicular to the plane. So first of all, what's going up like this? Well, first of all, we've got the reaction force of 68.6, and that's it. Because then the other two parts, the x sine theta down here is going downwards, or alpha. What do you call theta? And likewise, the weight component 5g cos alpha, which is down here, right? And I think that's all our forces, right? I'd say. So then again, the opposite direction would be equal in that direction. So resolving perpendicular. So then that's going to mean 68.6 is going to be equal to x sine alpha add 5g cos alpha. And so those are our equations, right? Now that's pretty much the hard part of the question. So let's have a look at what the question is actually asking us now before we do anything else. So let's look at part I. Find the magnitude of the frictional force acting on B. Okay. Are we given the coefficient restitution because it's a friction? Nope. Okay, so we're going to have to use these two equations to find F. But we can, because the only thing missing here is F and X. Because cos alpha and sin alpha we can deal with because we know what tan alpha is. We'll look at that in a second. So it's basically simultaneous equations. Okay, but I talked about, so I'm going to need to deal with the cos and the sine alpha. Again, this is a very common trick as well. We know that tan alpha is 3 over 4, so we need to construct a triangle. Okay, so that's alpha. So the tan alpha, remember SOHCAHTOA, TOA, we want opposite over adjacent. So the opposite is going to be here 3, and that corresponds to the 3, and the 4 will be the adjacent part 4. Now, with sine and cos, we need the hypotenuse, but the hypotenuse we can find by Pythagoras. Well, it's going to be root 3 squared and 4 squared, and actually put that into a calculator, you'll get 5. Okay. And now we're in a position, because now we're going to, well, sine alpha using SOHCAHTOA trig, well, opposite over adjacent, 3 over 5, and then cos alpha is adjacent over hypotenuse, 4 over 5. So now we can substitute those numbers in. Now, what you shouldn't do is try and well, I'll try and see what happens on the calculator, but don't just try and invert tan and say alpha's tan minus 1 or 3 over 4. Because what will happen is you'll get a nasty decimal. And then if you say sine alpha, actually, it might just. Oh, actually, in the calculator, it does get you back 3 over 5 if you then plug that nasty decimal to say sine of that angle. It gets you 3 over 5, and then cos of the angle. Okay. So if we are struggling, maybe, but this triangle, that should be your go-to, really, to get exact values. Anyway, so now we can plug this in. So now we can say, oh, that's x, by the way. So let's look at the first equation then. So x cos alpha, well, cos alpha is 4 over 5, so that's 4 over 5x. And that's going to equal f. Add 5g sine alpha, so sine alpha is 3 over 5. So it's 3 over 5 times 5, which is 3, right? So that's going to be 3g. There we are. So then the second one, 68.6, it's going to equal x sine alpha, that's 3 over 5x. Add 5g cos alpha, that's going to be 4g, because the cos alpha is 4 over 5 times 5, the 5's cancelled to leave with 4. Okay, well actually this one, the second one's quite nice, this one, because we can find x, and then we can find x to find f. But then x then is going to be well, let's break it down a little bit. So 3 over 5x is going to be 68.6 minus 4g. We can't do anything with that. But then x is going to be 5 over 3. 68.6 minus 4g. Does that simplify nicely by any chance? Uh, not particularly. Well, you get 343 over 3 minus 4 times 5 over 3 minus 20 over 3g. Okay. Um, Hang on a minute. What have I done here? Oh no, I've not done anything wrong. Okay, I guess that's just. I don't think anyway. I guess that's just how the cookie crumbles. Just the nasty number. So now we found x. Then we can use that to plug into the first equation. So that would then mean that f is going to be, what is it? 4 over 5 of x. So that's going to be 4/5 of 3, 4, 3 over 3 minus 20 over 3g. Uh, minus 3g. Okay. And so then if you put that into a calculator, about 4 over 5 of 343 over 3 gets us 1372 over 15. And then minus 4 over 5 times minus 20 over 3g is a minus 16 over 3, but then we have another minus 3g over here. So in total, we get minus 25 over 3g. Okay, so that's that f. Does it say to round it? The magnitude. That's really it. I think perhaps you can round it if you say g is 9.8. But that'd be the exact value. So g is 9.8. F then would be, and then I'm going to do it as like a decimal to 2 decimal places. Because I think it's a lot easier to visualize what's going on if you have a decimal. And I think the examiner should be fine with that, the rounding. And actually, you get a nice number of 9.8. That's interesting. That's G. That's really interesting. That is right though. And it's 9.8. Um, cool. So that's what I did. So when I substitute 9.8 in for G, I get this. And I think F might, maybe, I don't know. Uh, nice coincidence, I guess. There we go. That's F for 3 marks. So wow. And then part B, the second part. And actually, this is quite interesting. The second part, because it's talking about what I said earlier a little bit. State the direction of the frictional force. Now, actually, this time I got positive. So what I said about the fact that the horizontal force is pushing it up. So then F will go downwards opposed to motion because friction essentially always wants to counteract where something is moving, right? So actually F is going to be down there. So it's going to be acting what the direction. So it's going to go to the left. I want to try be as specific as possible. Uh, so it's going to go down the slope perpendicular, parallel to the slope. There we are. So F acting downwards, parallel to the slope. Okay. So the direction, obviously, first of all, is it perpendicular? So if we have the slope here, is it perpendicular or is it parallel? Well, F is parallel here, but then is it going down or up? So it's going down. So that's our direction. Okay. Now I did speak about this earlier. I said, oh, what about maybe F could act out upwards instead? Maybe instead, uh, there's not enough of X to push it hold it in position. So there's still weight dragging it down, so therefore it's going to go move down the slope. So F would have to instead move up. If you instead assumed F went upwards, it wouldn't change much. The only thing at the end is you'll get a negative answer for F. So actually F would be negative 9.8. But then what that would mean is you'd assume the opposite direction would be positive, right? So F would instead have to move downwards, like we just did there. So then part two, if you had a negative answer for part A, then it would instead of going up, you'd assume the opposite direction. So it would instead be moving down like we did. Okay, but yeah. Okay, then it says the horizontal force of magnitude x is now removed and b moves down the plane. There we are. Given that the coefficient of friction between B and the plane is 0.5. Okay, so let's just restate this. What's going on now? Let's draw the new diagram. So again, it's going to look like this. Oh, not there we are. Something like that. We have alpha. we have our thingy, our particle, what you want to call it, B at B, and there's no X horizontal. So actually, it's a lot easier now in a way. Um, the reaction would still be it's a bit steep actually, isn't it? Let's draw it a bit. There you go. It's a little bit better. So that's our particle. Now, actually, a reaction force is still going to be 68.6 because that's not changed, regardless. Actually, no, it would. Oh, actually, it might actually. No, sorry, because we had the two components for X, so that it might affect the reaction now. But that's fine. We'll call it R. So reaction would now be R. It wouldn't be 68.6 because remember in part A, the reaction force, which is acting perpendicular. Remember, X also had a perpendicular component of X sine alpha. That's gone away now, so that will adjust at R throughout the reaction. Okay, so that's the reaction. Now friction. Now it's moving down the plane, so actually acceleration is going to be going that way. So if it's going down, then again friction now has to be up here to oppose it. Okay. So again, we also have a weight again of 5g. So again, that's going to be an angle in alpha, so it's going to be 5g cos alpha, and then 5g sine alpha. That's all our forces actually. A much more simpler model, but now we have acceleration. But we're also given mu is a half. Okay, the coefficient of friction. So again, in the same sort of way, it's probably best to resolve again. So first of all, perpendicular. Now, so that just to be clear, that is perpendicular. So you're going to have R, the reaction force, equal to 5g cos alpha. Hopefully you can see that. Right, the cos alpha, the weight component here, is acting opposite direction. So down here, in opposite direction to reaction. Okay. And more specifically, it is accelerated. It's moving now, and the key thing to notice is moving. So there is when we use F equals ma, that's what we're using when we're resolving. Because when it's at rest, A0, so that means the resultant force has to be equal either side, right? But because now it's moving, there is an acceleration, so we're not gonna necessarily equate both direct opposite directions as the same. But because it's not moving, it's only moving parallel to the plane. It's going down perpendicular. There's no movement perpendicular. It's not moving up. Okay. Oh, okay. What was I saying? But yeah, there's movement parallel to the plane, and it always be like this, right? If it's moving down or up, acceleration at parallel, but then it's not going up really. It's not going to go parallel, so the acceleration, well, there's no acceleration, there's no movement in that direction. So specifically perpendicular, it's still going to be the opposites will still equal. So R will still be 5g cos alpha. But this is where the perpendicular gets interesting. So if I'm going to resolve downwards now, so then well, what's acting downwards? Well, there's 5g sine alpha is down here, right? Um, and then what's acting upwards? And also, I'm taking downwards to be positive because acceleration is going to be positive down here. It's a wise decision to make in this particular case. Make acceleration go in the direction of acceleration. So if I just sine alpha, although it doesn't matter, but But then F is going to go the other way around, isn't it? So it's going to be minus F of friction, and that's all our forces, right? Um, but this is not going to equal F, it's just going to be minus, because this will now give a resultant force, RF, right, something like that. And this resultant force will equal MA, okay? But we know M is 5, so it's going to equal 5 lots of A, the acceleration A, okay? So it's not equal to each other, it's not equal to 0 now. There is acceleration at play, so that's the key thing to remember here. But now we've got our equations again. So again, we've also got another equation, haven't we? Because we've got F equals mu R. But mu is also a half, so it's going to be mu R. Okay, so we've got three equations, so it's like simultaneous equations now again. That all these questions work in the same way. Just get all your resolving equations or moments if relevant, and then just work with it to solve stuff. Essentially, it's the same thing every single time. The hardest thing, obviously, is then spotting where the forces are and how to resolve. But once we've done it, it should be fairly standard. So I've got R. So this can be computed because we know cos alpha again is 4/5. So we know that R is at 4/5 of 5, so it's going to be just 4G. So then F is going to be half of that, so it's going to be 2G. So then therefore we can then compute A, because then we can say, well, oh, 5G sine alpha, again, sine alpha is 3/5, so it's going to be 3G. This will go to 3G, minus F of friction, so it's minus 2G, is 5A. Therefore, 5A is simply G, so A is a fifth of G. And there we are. Cool. There we are. That's nice for 6 marks. I feel that's a lot simpler than the first question. I don't know if it's just me, but that was 6 marks, but this was only 4. And really, the actual main bit was only 3. I don't know. I don't know, but yeah. A standard sort of question. I'll try and get your head around that. If you haven't already. But this question's typical, comes up all the time. But yeah, cool. Question 3. Okay. I wanted to go over this sort of question. Again, now we're dealing. Well, let's read the question first. A particle P of mass 4 kilograms is at rest on point A. At time t0, two forces are applied to F. Given that P moves in the direction of this vector, show this. Okay. So, right. So what you need to recognize is that acceleration, although it's going to be a vector, it's going to be a constant vector. So acceleration is going to be constant. Why? Let's explain. So we've got given two forces, so you should know that the sum of them, the resultant force, F1 and F2, that's going to equal ma, right? That's just an extension of F equals ma in the vector world. Okay. But again, we know this. The mass is 4, so it's going to be 4a. And they're all going to be vectors, F1, F2, MA. Okay. But then F1 and F2 we can compute. F1 and F2. Well, F1, again, I'm going to use it as a column. It's going to be 4 minus 1. And then add F2 is going to be lambda and mu. And that's going to equal 4a. Okay, but we don't know anything about A, but we're also given that P moves in the direction of this. Now, usually when they give you something like that, something's moving in the direction of a vector, that's telling you the velocity vector is in this direction. But we don't know anything about the velocity. However, we are given stuff about the force that acted on it. Now, the overall force is still acting in the same direction, wouldn't it? Because overall, the P is being pushed by the resultant force in the direction of the resultant force, right? The resultant force is dictating where the particle goes. So in this case, well, actually, the result of the sum of this. So I'm going to bring it together. Say 4 add lambda minus 1 add mu. If we add the two vectors together, that's going to be in the direction of this vector 3i plus j. Now, in the direction doesn't mean it's equal to the vector. It's saying it's parallel to it, right? Um, so if it's parallel, remember two vectors parallel is the same direction, um, essentially. But if they're also parallel, that means they're going to be a scalar multiple of each other. So this is going to be equal to k lots of this vector 1i and 3j, okay? Because that essentially means they're in the direction of it, it's parallel. Oh no, it's 3, 1, sorry, not 1, 3. And so essentially, we can sort of, again, get simultaneous equations. Mechanics is all about simultaneous equations. It's all about it. So we can deduce, if we add the top component, for lambda, it's going to be 3k. And then I'm going to say mu minus 1 is going to equal k. But let's have a look what they want us to get. We want to get rid of this k, don't we? You just want a lambda and mu. So we want to get rid of k. Well, I think it's best to substitute it into this into here. So therefore, k is going to be mu minus 1. So forward lambda, it's going to be 3 lots of mu minus 1. Okay, I just substituted one into the other. So forward lambda then is going to be 3 mu minus 3. So I'm going to move it all to the left. It's going to be lambda minus 3 mu. It's going to be plus 7 equals 0, right? And hopefully that's what they got. Yes, there we are. 4 marks, not too bad. Okay, then it says at time t is 4, t passes through the point B. Given that lambda is 2, find the length of AB. Okay, I'm going to ignore this because I know this lambda is 2. Substitute in here to get mu. Okay, so before we do anything else, we can pick up some 3 marks there. Say, well, lambda is 2. Therefore, 2 minus 3 mu, substitute it into this equation, add 7 equals 0. So 3 mu is going to equal 2 plus 9, so mu is going to be 3. Cool. And then I could also then work out F2 if I need to, but let's have a look. Okay, what's going on here? So let's go for the length of AB. So we have A here and B here, for instance. Doesn't matter exactly where, just a little diagram. So I want A to B. Okay. Uh, right. But this is going to be Suva, isn't it? Because we're dealing with time, and actually we've got acceleration here. But given that it's at rest initially, so that means U is going to equal 0. Um, we know we're going to find out. We know the time is going to be 4, right? Between 0 and 4 and 0. Um, and we want the displacement R. Anyway, we'll deal with that in a minute. But what we then can work out is F1 and F2 is equal to 4A. Okay. So then F1 and F2, remember, is 4 add lambda. And lambda's 2, so it's going to be 6. And then minus 1 add mu. So mu's 3. So 3 minus 1 is 2. And that's going to equal 4A? Yes. So therefore A is going to be a 4 of 6, 2. And again, you just divide each part by 4 or times each part by a quarter. Either or, you should get 6 over 4, which would be 3 over 2. And then 2 over 4, which should be a half. Right, okay. Okay, let's go back to this diagram. So now we know that A is 3 over 2, a half. And that'll be constant, okay? So that means if we have a constant acceleration, we can use Suva. So let's list what we know between A and B. So S, we actually want to work out what S is. U, well, it's initially at rest at A, so U is going to be a 0 vector, which is just 0, 0. Okay, that's U. V, we don't care about, but we don't know anything about the velocity at B. A, we know is 3 over 2, a half. and T we know is 4. So actually we've got the ingredients to work out S. And in this particular case, unlike variable acceleration this time, variable acceleration, the displacement R gives you the position vector. With constant acceleration in this case, the value of S or R that you get, it gives you the displacement travelled between the 2 points. In other words, AB. It does not give you the position vector of B this time. That's one of the most essential things you need to get your head around with regards to these sort of kinematic vectors. The difference between variable and constant acceleration. The variable gives you the position vector for the displacement, and the other one, in this case, the constant, gives you the displacement travelled, so the vector between the 2 points. Okay, that it works nice in this case because we just want to work out what AB is. We're not interested in position vectors. Um, we want. So I'm going to say it again. S we don't know. U we know 0. V we don't care about. A is 3/2, a half, and T is 4. Okay, so the Suvat formulas are in the formula book. So which one ignores T? Let's have a look. Let's go to the mechanics section. Let's have a look. Which one ignores T? Right, it's this one, isn't it? This one has no V in it. So we're going to copy that down. So S is UT plus a half AT squared. And then we just substitute it in. So then we can say S, it should be a vector, but it doesn't really matter. Call it S or R, doesn't really matter. UT, now U will go to 0, lots of T, so that would just be nothing. So it's going to be half of AT, so 3/2, half. T squared, which is 4 squared, which should be 16. Okay, that's quite a nice vector to work with. So this will be, well, 16/2, that'll be 8 lots of 3/2 a half. And that will go to, if I times 8 inside, both parts. So 3/2 times 8 will get us 12. And then 8 times a half will get us 4. Cool. Now it wants the distance AB. So this is actually AB in vector form, but we want the distance AB. So length of AB then is going to be the length of this vector. So it's going to be the modulus of 12 squared, or the plus 4 squared, and that in the calculator should get you root 12 squared at 4 squared will get you 4 root 10, and that's your distance there. Cool. There we are. Lovely question that is. There we go. So that's the length of AB. Cool. Okay, question 4, a bit of a harder one, harder diagram question. Let's have a look. Again, a pretty typical one. A uniform rod AB has mass m and length 2a. Particle of mass 2m is attached to the rod at the point C. The rod rests with its length m, rough horizontal ground. The rod held in equilibrium again by angle alpha. Okay, it's pretty standard stuff. So again, let's label our diagram. So uniform rod. Uniform, first of all, means the rod will have a mass. Now, a rod, uh, the rod isn't. The rod is weirdly like another particle in a way, but it's like a one-dimensional particle rather than just being like a circle like this, a single point. So it has its mass, because it has a mass of m. But weirdly, that means also it doesn't have to be a reaction force on stuff on it, you know. Therefore, we have two particles here, but there's going to be no reaction force at C because it's a rod, and anything that isn't the surface touching the rod. So this isn't the surface; it's the particle. So it's going to have no reaction force. But this is a surface. This is a wall, isn't it? I think. Let me have a look. Oh, it's a string, so that's going to have a tension. There we are. That would be tension, but there'd be no reaction. But here, this is a floor. I think, ground, and it's a surface, so it will have a reaction force at this point A, not because of the rod, but because the rod is touching the floor. Uh, if that makes any sense, the rod itself necessarily isn't the surface. Well, it basically isn't. It's based like another particle. So it itself, if it touches another particle or whatever, won't have a reaction. But then if it touches again, just like a normal part, like in the other question, if it then touches like a surface, like an inclined plane, for example, like we saw in the other question, where we had that particle, right? It will have a reaction force because it's touching this surface. In the same way, this ground is now a surface at A. So when it touches the ground, it will have a reaction force, and I'm going to call it RA. This ground is also rough, so it's going to have friction. Now let's have a think about this. So imagine it's being held in equilibrium, but think about it. It's going to kind of slip this way, isn't it? This rod thing is going to slip that way. Um, and the only thing that's stopping it from slipping at the moment is the tension that's pulling it up here. But it wants to slip this way. And again, that's going to be because if you have the weight here of the particle, now this particle is 2m. Again, this is going to be a theta here. Though the weight is going to cause it to move this way, isn't it? So the force then, if it wants to go that way, the friction is going to act this way to oppose this. Okay. But that's not the only thing. This tension as well. If we resolve it, so if we have it, that's already perpendicular. Um, but never mind. I don't want to talk about that. But that's going to be alpha here. Um, but essentially, the stuff that's going to force it to move to the left, isn't it? Because this force here is going to go to the left direction here. The weight component, uh, uh, parallel to the slope. Um, so yeah, so the force will go the other way, and usually the friction will act this side anyway. But yeah, the friction will be that way. Okay, then I did talk about this particle here. This will have a mass, no reaction, but will have a weight. So straight down is 2m, so this is going to be 2m cos alpha. Again, theta now. Um, and again, the angle theta will be this way, and then this will be 2m sine theta. Okay, but there's also going to be a another what's it called? Another mass because the rod itself of the mass again it's kind of like a particle, so it have its own mass. But it says it's uniform, so that means the mass is like evenly distributed along the rod. What that means is we can assume the mass basically in the middle of it. That's where the mass is, because then on either side it cancels out in a way. So then we can attribute the mass of the rod as just being in the middle. But the middle, where the whole length of AB is 2A, so I'm going to draw it here. Oh, it's a bit off the screen. The whole length is 2A. So, and we also know, do you know if AC is a fifth of A? So if we draw it here, for example, where this mass is going to be of the rod, it's going to be mg, and it's going to be halfway, right, to be the middle, and then this would be 0.5a, and then that'll be another 0.5a. Okay, because A to C is 1.5a. Hopefully, you can make sense of the distance there. And again, if we have to resolve, well, we could resolve it if we wanted to. So it's going to be theta again. It's going to be m cos theta. I have to squeeze it in a little bit. M cos theta, M sine theta, and that'd be that way. Okay, and I've got and that's I believe all the forces actually. But what we have here is if we ignore what I resolved here for the masses, for the weights, because of the signs, every other force is actually just directly up or left or right, apart from this tension here. And so if we were to instead resolve up the plane and parallel perpendicular to the plane, our tension's fine because it's already perpendicular here. But everything else we're going to have to resolve to make it parallel perpendicular, especially the friction and the reaction. Because the reaction is not perpendicular to the plane, it's perpendicular to the ground. Okay? Or the rod, I should say. It's not perpendicular to the rod, it's perpendicular to the plane. Not the plane. The ground, because it's the reactions from the ground. So we have to resolve everything else apart from T. That's going to be a massive ache. So actually, what I'm going to say, you can keep this if you want, but I'm going to get rid of resolving the weights and just leave it as it is. Because hopefully you can see clearer that we've simply got loads of forces going up or down and left or right, which will make it a lot easier to resolve. Apart from T. T is the only thing we have to resolve. And so where's that going to be? So again, so we're going to resolve it up and down and left or right. So we're going to, so this perpendicular, but we have to create a straight component this way, and then let me scroll up, and then another components directly left, right? So here and here, and that would be our direction, and that would be a right angle there, because obviously left that should be perpendicular there. Okay, but now we need this. We need a theta somewhere. Now that's probably going to be the tricky part of this question. Where's this theta going to be? Um, And again, we got to consider Z angles. So we have this here, this plane here, and we have it going to be here. We have the angle theta. Um, Now, actually, if we then consider, because we need this to be parallel here, let's consider another, just add a line that is also parallel. That means this angle has to be a theta. That will correspond, if we then draw it like that, to this angle here being theta. But actually, then that would mean because these two angles combined add up to 90 because we've got the right angle here. Uh, oh God, I've got rid of it now. There we are. This will mean this was 90 minus theta. Okay. Um, yes. And so actually, we've got another right angle here. So if you notice here. So this angle then is going to be well, it's going to be 180, no, 90 minus 90 minus theta. So 90 minus 90 would be 0, and then minus and minus theta would be just theta. So this angle then has to be theta. Okay. Um, so that's probably a really tricky way of labelling the angle, but you should spot the angle particularly here then if we have this triangle for tension. Oh, so T is acting that way. This angle will be theta. Okay, a lot of labelled here. So that's going to be theta. Okay. Yeah, that's a really tricky way, I guess. I've seen that. Hopefully, again, you can spot this angle then. At C, well, not C, but here's going to be theta, near C anyway, there. And then if we draw like a parallel line here, cut it off at B, then the other angle up here is going to be 90 minus theta, because then that's the right angle. But then we have another right angle between here and then the two component and then this component. So that means this is going to be theta. Okay. That is probably quite tricky, but hopefully you can get your head around that. And that's sort of the thing you want to do if you're struggling to label angles. You're going to have to consider like some Z angles you can make um, here, and then maybe like we did here, use angle facts as well to then work out other angles to an angle that you want inside the triangle. Oh boy, so I'm gonna get rid of one now. It's a bit messy, but we've resolved it to an up and a left and right component, which is what we want. So let's get rid of all this again. Oh, it's not the straightest triangle, is it? So it's gonna be there and then there. There we are. So tension's gonna be there. So theta is now going to be there. So that means if we result, this is going to be t sine theta, and this is going to be t cos theta. And now what we can resolve up, and we can resolve to the right, okay? And there are two where resolving when we've got two dimensions, there are two directions to resolving. And mostly in mechanics, you can either resolve perpendicular and parallel to the plane, because these are opposite directions, right? They're both 92 degrees to each other. But we can only do it in two directions. Or alternatively, like we can do here, if everything's in up or down or left or right, you can simply resolve straight up and then straight to the left. Okay, oh man. There we go. So we've got all our forces resolved now to up and down. Like I said, if you did the other way and resolve perpendicular and parallel, you'd have to resolve all the weights and you'd have to resolve F and RA. I don't fancy doing it. Was hard enough trying to get this T angle, this T resolved. But yeah, there we are. And that's the hardest part of the question, really, I think. Again, just resolve and get all the forces down. Okay, then in part A, so explain why the frictional force acting on the rod at A acts horizontally to the right. Oh, it tells you it's to the right anyway, but why? Again, that's because of the slipping. And that's because there are forces. So I'm going to say the rod will slip to the left as, and let's have a look. Again, let's have a look at our resolved forces. So this is going to act up and then down here. But first of all, the tension as well, because the tension to the left is pushing it that way. Same as the weight. If well, oh no, there is no weight left, but the tension, particularly straight left, the tension up here, the T sine theta, it's acting this way. So it's going to push the rod to move this direction, isn't it? Because it's both going to the left direction. So it's being pushed to the left, specifically by the tension in the rope. So friction will oppose this motion by acting to the right. Yeah. So the opposite direction to oppose the motion. Okay. Part B. Um. The tension in string is T. Okay, so now we need to solve. We need to get some equations. Okay. Uh. So firstly, we aren't given mu at the moment, the coefficient of friction. So the only thing we can do is resolve up and down, left and right. But also, there's going to be moments. Uh, and why are we doing moments here? Because we want to because we have a rod essentially, and moments is better with rods. Because like I said, rod is like another particle, but it's a line. So we all these forces here will push the rod anti-clockwise and clockwise. So there will be moments as well. And again, because it's in equilibrium, the moment will be equilibrium as well. And the other reason as well is because we've got loads of unknown variables. Whereas the other example, we only had the friction and the horizontal x force unknown. So we have two unknowns. So we only need two equations, which come from resolving in two directions. Here we got loads of unknowns. But anyway, so the first bit, let's just resolve, I guess. So let's resolve upwards. So what's acting up? Well, you've got the t cos theta up here. And we got the result of force RA, and that's really it. So T cos theta and RA. Um, what's going down? Well, the masses, aren't they? And this will be 2 mg, I forgot to say. Well, what's adding downwards is just these masses here. The mg and the 2 mg, the weights, right? The mg and the 2 mg. And in total, that'd be 3 mg. Oh. Then we're going to resolve to the right. So what's acting to the right? Well, the friction right down here, and then the only other force is the t sine theta here, and they are opposite directions. So F is going to equal t sine theta. But we're also going to take moments. So I'm going to say but now this is what revolving, I guess, in the anti-clockwise direction, which I will specify here. And I'm going to say resolve at a point. And actually, what's the best point to take? Where are we going to take moments along the rod AB? And the best thing to pick is the place where there's the most forces going on. And that's going to be at A, okay, because we've got friction and the reaction force. At any other point, single point on the line, well, this is just a single force, this is a single force, and the tension is just a single force at B. So it's best to eliminate as many variables as we deal with, because if we choose A to take moments, we ignore all the forces at A because they have no distance. So we're going to take moments at A, and that's usually the best shot with these sort of questions, is to take moments there. So we're going to take moments at A, and so the moments is consider what goes anti-clockwise, uh, and the best way to work that out is actually use a ruler again, but well, last time I tried to use a ruler on here, well, the last few, it just never worked for me. Maybe it'll work this time, I don't know. So assume again the ruler is the rod. See, this was so annoying. Okay. Oh God. Okay, something like that. I don't. There we are. Okay. So if we then how we can work out the direction of the moment. So basically, the when each force is pushing it anti-clockwise or clockwise, the ruler. So we fix the ruler at A, and then imagine of each force. So you're going to have to consider the perpendicular direction of each force. Moment, remember, is distance times the size of the force. However, the force has to be the perpendicular component to the line. So T is already perpendicular, but we're going to have to consider instead, we're going to have to resolve the weights. So consider the perpendicular component to the line, to the rod. So that's going to be theta. So this is the perpendicular component. So that's going to be 2 mg cos theta. And again, this is theta. This could be mg cos theta. So that's the perpendicular component. So how do I explain this? It's really hard to explain in this sort of format. But imagine if you line up the ruler and you hold it at A. Okay, imagine I'm holding the ruler here and fixing it at A. Then imagine you push the ruler down um, at the perpendicular force. What's going to happen to the ruler? The ruler is going to tilt clockwise, isn't it? It's going to go this way if we keep pushing the ruler down here. It's going to go clockwise. And hopefully you can see that if you keep pushing it down there, if you hold it, well, I'm not holding it here, but hopefully you can see it's being pushed clockwise. It's turning clockwise. Um, and that'll be the same for this here as 2 mg, the weight as well. What about the T? Well, the T, again, if you hold it A, it only goes one way, this ruler. I'm not doing it all again, but it'd be a different sort of argument. Again, if you have a ruler, put a ruler AB, hold your finger at A to fix it A, then use your other finger to then push it in this direction T at the ruler here. What you should notice is the ruler will then tilt anti-clockwise, so it'll move in an anti-clockwise direction, and that will give you the direction of the forces and the moments they are. So the anti-clockwise then, I know that probably it's hard to explain visually. It's so easy in person, but obviously it's really hard to explain online like this. But so the horizontal. So firstly, the T, the tension will force it anti-clockwise. That's where we want. So anti-clockwise is going to be this sort of motion, and the clockwise will be the opposite. It'll go like that. Anyway, so anti-clockwise at A. So that's going to be the side of the force perpendicular to the rod, where T is already perpendicular. There we are. So it's simply T. And then we want the distance, and that's from A. So that's going to be 2A, remember? AB is 2A. And so then we want to equal the clockwise component, right? So the clockwise forces, well, that's going to be mg, first of all, here. But remember, this is middle of the rod, so that's going to be just A, or 1A. So it's going to be mg times A, and then 2 mg. But then that'd be cos theta, wouldn't it? So mg cos theta is the perpendicular component times A. And then we want the other weight, 2 mg cos theta, because that's the weight of the particle at C, which is 2 mg cos theta, times the distance, which is going to be 1.5a. So remember, there's another 0.5a after the middle. So that's 1.5a. And there we are. Actually, I'm going to simplify this then. So, again, we can simplify all the causes and sines by using another tree. Not tree. Another diagram. A trig diagram. There we are. With this theta. So again, we have the theta here. That's gonna be right angle. We know that tan. Does it tell us? Oh, it doesn't tell us. Oh no. Okay, we can't do anything with that then. Yeah, because it's telling the cos theta. Okay, we can't do anything with the angle then. So all I'm going to say is actually simplify this equation a little bit. I can cancel out the a's, can't I? Actually, because a's are common in all three of them. So that means 2t is just going to be mg cos theta. Add 1.5 times 2 would be 3 mg cos theta. And in total then, 2t is going to be 4 mg cos theta. And actually, we could solve this to then say, well, t is going to be 2 mg cos theta. Actually, is that what they wanted? Yes, t is 2 mg cos theta. There we are. They did that question without even specifically going after it. There we go. So then part C, again, we probably have to use the other resolving. Okay, cos theta is 3/5. Show that the magnitude of the vertical force exerted by the ground. So we need to find RA essentially. Because A is the vertical force, remember? The vertical force at A. So we want RA. So to get RA, again, we have to use our equations again to solve for RA. But we also know then that cos theta is 3/5 now. So if we construct our triangle, that's going to be theta. So cos is SOHCAHTOA, so adjacent 3/, hypotenuse 5. Again, that would be 4 by Pythagoras. So therefore, sine theta We don't need tan. There's no tans. You don't really need tan usually. But sign and card, well, sign is opposite, so it'd be 4/5. Okay, then for part B, now we know, well, firstly, we know what t is as well, because we know in t, we know cos theta now. That's going to be 3/5, so it's going to be 3/5 times 2 is 6/5 mg. Okay. So now we're going to use these two equations, right? So we know that f is t sine theta. Well, t is 6/5 mg times sine theta is 4/5. So that's going to be 6/5, 24/25 mg. So that's like f, and then we can use it to get the last bit, the other equation, t cos theta. I'm not good at sub cos theta and intercept, so I'm going to rewrite the equation. And Ra is 3 mg. So then cos theta was 3/5, so 3/5 of t. But again, we know that t is 2 mg cos theta. No, t was 6/5 mg, sorry, we simplified it. Add Ra is 3 mg. Okay, well that goes to 3/5 times 6/5. That's 18/25 mg plus Ra is 3 mg. Therefore, Ra is 3 mg minus 18/25 mg, and that will simplify to 57/25 mg. Um, and that's what we've got. So 57/25 mg. Cool. And that'll be the magnitude of the vertical. Sometimes they do. I think if I have time, I'll do another mechanics paper, and I think some questions that ask for the in this sort of question that ask for the magnitude of the force, not the vertical, just the overall force acting on the ground at A. So if we were to enter the force in total at A, remember at A there's two forces going on. You got a friction force and a resultant for reaction at A. If you want to find the overall force at A, not just the vertical or the horizontal, again you do the Pythagoras here. Um, no, sorry. Uh, Here, something like that. And so therefore therefore the length of this, obviously that's going to be the Pythagoras. So that's also going to be Ra, right? So therefore, you do if you want to find the length of this overall force here, that's the resultant force, right? You'll do Ra squared add F squared, friction squared, and square root it, right, to get the resultant force. Um, but here, pay attention. Only ask for the magnitude of the vertical force, which the vertical force is just Ra because it's acting off. So friction's not involved. The friction is acting parallel. It's acting horizontal. Anyway, then it says the coefficient of between the rod and the ground is mu, and the rod is a limiting equilibrium. That means then we got this equation: F equals mu r, and mu is going to be F over r to find mu. But we also know we already know what the friction is. Friction F is 24/25 mg divided by r, which we found to be 57/25 mg. Now again, the mg's cancel, but if you've got a fraction like this, obviously you probably could put it in the calculator, that's fine. But this is saying 24/25 divided by the fraction 57/25. So therefore, you do KFC, keep, change the sign, flip the second fraction, and that will go to 8/19. And that'd be the same if you just want to plug that in the calculator. This bit you'll be fine as well. But therefore, mu is 8/19. Okay, cool. Okay, there we are. Right. And see how like creating those forces at the start. I think that's a good strategy to always do, right? To get all your force equations, so result up and down, perpendicular, parallel, depending, do your moments if necessary. If you get all those equations at the start, you set yourself up really, because then we could work out these three questions very quickly after that, and that's what 10 marks worth for just those three equations. But yeah, the hardest thing again is to realize to resolve and work out where the forces are. But again, these scenarios are the same every time. There are only so many different different force scenarios that the Edexcel can ask you. And that'll be in the textbook as well, actually, all those different type of questions we want to practice or past papers. But these questions come up every single time, pretty much. Um, but yeah, so once you practice them and learn where the forces are, like for this, if you use this video, for example, then you can practice for future questions like this. Okay. Cool. Okay, that's question 4. Question 5. Okay. Um. Okay. So we are told a golf ball is at rest at a point A on horizontal ground. The ball is hit and initially moves at an angle alpha to the ground. The ball first hits the ground at the point B, where A, B. Okay, so they're giving us all the information there, and the speed is u. Um, okay. Using this model shows something. Okay, so again, like with the force diagrams, what you should always do with these sort of projectile questions, again, you want to not resolve, but you want to use all the pseudo information you can get. So what happens in these sort of questions is it's pseudo in two directions. So it's going again like the speed we can resolve parallel and perpendicular. So this is out. So we use sine alpha, and that's going to be u cos alpha. And also, it's going against gravity, so it's the gravity down here, and that will be your acceleration. So so the acceleration upwards will then be minus g. Okay, and that's all you really need to be aware of essentially. If you do that, once you do that, what you then want to do is instantly, pretty much, you want to split this up into horizontal, vertical and horizontal. And then what you want to do is smooth out on both of them. So vertical SUVAT and vertical. Well, we don't know the vertical displacement or the vertical distance, right? Between A and oh no, we do. Sorry, A and B are both on the ground, so the overall the displacement is 0. So that's the vertical displacement. Notice I say displacement. Okay. So the displacement is the overall difference of vertical height between the start and the end. But here there is no difference between the start and the end because they both start on the ground and the end on the ground. So the overall displacement is 0. U again, the initial speed will be u vertical is going to be u sine alpha. That's going up. So u sine alpha. If it helps us solve vertical, go that way. Horizontal, we're going to go to the right. So V U will be u sine alpha. V we don't know anything about. Let's leave it. That acceleration will be minus g because we're taking up to be positive, right? Because the speed is going up. So g, the acceleration, gravity is going down, right? So if we're going up, so then we're opposing the gravity, so it's going to go minus g, and that will always be the same. Always be minus g. Okay. If you're going that way. And T, again, we don't know anything about. Let's leave it. We don't know two things. Okay, that's fine though. Horizontal then. Now, horizontal is a lot more simpler. We don't actually need to do that because as we kind of like I would talk about before about the resultant forces with F equals ma. In one direction is always zero, and it would only move down, accelerate in one other direction. It's the same sort of case here. The acceleration only acts vertically. There is no acceleration horizontally. So horizontally, there'll be no acceleration. That means the horizontal speed will always be constant. Okay, you can think of it as like integrating zero, because remember acceleration integrate to get velocity dt. That's going to be zero at c. Well, c we don't know, but c is a constant, so that'll be your velocity. So the velocity will be constant. Okay, but we know what the speed is. It's u cos alpha. That's acting horizontally. So we know, well, we know s is 120. U we'll get to speed v in general would be u cos alpha, and t we don't know. But that's where we can start off actually. And the good thing with this is when you got constant speed or constant velocity, not just acceleration but constant speed, all you just need to know the G3 formula, distance, speed, and time, right? So horizontally, you can just say distance, speed, and time. Then that's going to be some value t. That'll be when it hits A and B. The time vertically and horizontally will be the same, right? Because they will hit A and B at the same time. So the t will be common both vertical and horizontal. So if we can work out an expression for t here, we can substitute that into here to solve stuff, right? Anyway, so that's what you want to do all the time, essentially, this sort of projectile question. Label your vertical and your horizontal parts, okay? Um, and yeah, so a horizontal, again, probably the best bit here, because we work at the time. So that's going to be distance. Remember, the distance was 120 horizontally. It says it in here. There we are. So distance is speed times time. So that means 120. And again, at this point, it's just going to be simultaneous equations again to like solve stuff. But 120 is going to be speed, which is u cos alpha times time. So therefore, we can rearrange to say t is going to be 120 over u cos alpha, and then we can substitute it into here vertically if we need to. But yeah, so then we need to substitute in here, but here we need to do that. So we actually don't care about v really at the moment, but we have s, u, a, and t. So again, we need the Suva formula that avoids v, the final velocity, but we know it's going to be s is ut at a half 80. So that's in the formula book, but we already used it earlier. So then zero then for the displacement vertically is going to be ut, which is u sine alpha. Remember that's the vertical initial speed times t, which is going to be 120 over u cos alpha. Alpha, sorry, not theta. Add a half 80 squared. Now a half is going to be a, sorry, is going to be minus, so it's going to be minus a half g times t squared. It's going to be 120 over u cos alpha all squared. Okay. Um. So let's simplify this. So I think it's best to move to the other side. So I'm going to say half. Well, g. Notice in this question they don't say g anywhere. Um. So you're going to take g to be 9.8. Here, sorry. In our answer, there's no g. And the g. So we're going to take g to be 9.8. Therefore, a half of g. That's half of 9.8. It's going to be well, 4.9. So 4.9 of 120 of u cos alpha squared That's going to equal u 120 u sine alpha over u cos alpha. Then let's expand the bracket. So 120 squared times 4.9 will get us 70560 over uh, u squared cos squared alpha is going to equal 120 u sine alpha over u cos alpha. Then I could cross multiply, right? So then I could say 70560 u cos alpha is 120 u sine u cubed sine uh, sine alpha cos squared alpha. Then let's divide by 120. So you get 588. Yeah, and then they're going to divide by u. I'm allowed to divide u because if I'm divided by u, I'm saying u cannot be zero. But obviously u can't be zero because it has to have speed. So 128 cos alpha is going to equal 120 u squared. Oh, that would just be u squared because it's divided by 120. So that'd be u squared sine alpha cos squared alpha. Um, so then if I move it again, u squared sine alpha cos squared alpha minus 588 cos alpha equals 0. I can factor a cos alpha out and say that cos alpha of u squared sine alpha cos alpha minus 588 equals 0. Well, either cos alpha equals 0 or u squared sine alpha cos alpha equals 588. Now, actually, that's what we got in part. That's what we want to show. There we have for 6 marks. Cool. Uh, but we need to reject this somehow. So what happens when cos alpha is 0? Uh, well, cos alpha is 0. Well, then that would mean uh, cos inverse. Well, it'd be pi over 2, right? So it'd be pi over 2. I don't care about the other solutions really. It's not, but we'll leave it as there. But it'd be pi over 2. Okay, so it's but it's saying, well, really, cos alpha is 0. Think about it in terms of the speed. Cos alpha is 0. That means u cos alpha would be u of 0 equals 0. That's saying, therefore, there's no speed at all. It's not moving horizontally. But then how on earth did they get to 120 meters? That cannot happen. So that we have to reject that solution. So if u equals 0, then what's it? The particle? What did they call it? What's the thing that's been flung? The ball. Okay. Then the ball would not move horizontally. Uh, but we know it must. It must do in order to travel 120 meters, right? Horizontally. Because if you can't move, how are you going to move 120 meters? So therefore, cos alpha cannot be 0. So therefore, u squared sine alpha cos alpha has to equal 588 only. And there we are. U squared sine alpha cos alpha is 588. Uh, cool. So then it says the ball reaches a maximum height of 10 meters above the ground. Okay, so now we've got another situation going on. So then if the maximum height is going to be up here, isn't it? And that's going to be the maximum vertical height of 10. That's what he told us. Okay, so we've got another condition. So I'm going to call this point P. Okay. So again, we're going to do another sort of resolving session. So vertical suiver uh, upwards. I'm going to say from then A to P. What I should have done here as well, actually, I should have specified. Well, we don't have to specify, but to be really clear, this should have been upwards from A to B and horizontal from A to B. But it doesn't really matter as long as you know what values to put in. But anyway, so then if we resolve vertically, it's again S is going to be 10 now because the maximum height was 10. U is still going to be U sine alpha. That's the vertical initial speed upwards. V now V actually we know to be 0 because when it's at the maximum, it's at a point where it's the particle keeps slowing down, right? It's slowing down and slowing down and slowing down until then it reaches the maximum high, and it's kind of like do a move up. It's transitioning from moving up to moving back down because then it moves down. At that point, which is the maximum height, that's when it starts to go from positive to negative. So starts to go up to going down. So at this point, the velocity, the speed is 0. Alternatively, you can visualize this as a sort of like distance time graph. No, sorry. Yes, sorry, like a displacement time graph in a way, because this is like displacement up here and here. That's a horizontal, that's the vertical. And obviously the turning, so the gradient of the curve would represent the velocity, right? Uh, but if it's then 0, because that's when it's flat here, gradient 0 is a turning point, and the gradient of 0 means the velocity has to be 0, if that makes any sense. But essentially, it's transitioning from going up to going down. In that instant, the velocity has to be 0 to transition from going up to down. So that means that final velocity at P would be 0. A again is going to be minus G, that's going to be constant. And T, we don't know anything about T, but that's fine because now we've got an expression. If we were to do horizontal, we don't know if we were to. We have S, we do not know the horizontal. We know obviously U is going to be U cos alpha. So that's a constant speed, but T we don't know anything about either. So the only equation we can work with is this. Okay, this is the vertical suiver. And now we want to avoid T. So we want the vertical suiver without T. So which one is it going to be? This one. V squared is U squared of 2AS. So then we substitute it in. Those V squared can be 0. U squared is U squared sine squared alpha. 2AS. Again, G is going to be 9.8. So that's going to be 2 times minus 9.8. It's going to be minus 19.6 of S, which is 10. So therefore, U squared sine squared alpha is going to be 196. Okay, so now we've got another expression. And actually, we've kind of got simultaneous equations here because we've got one equation with U and alpha, and we've got this one for U and alpha as well. So in theory, we then can now solve this. But what do we need to do? Do we need to find V? U squared, not V, sorry, U. And we need to show this, U squared. Okay, let's do that then. So let's rewrite the equation then. So we've got U squared sine alpha, and we also know that U squared sine alpha cos alpha is 588, something like that. Yes. So we need to solve these then. So what we're going to do? Well, we want U. Um, Interesting. Well, I think immediately because I can divide. If I label as 1 and 2, I can divide 1 by 2 to get rid of u squared to be left with alpha somehow. So then sine squared alpha. Oh, I guess specifically u squared sine squared alpha over u squared sine alpha cos alpha would equal 196 over 588. Right, the u squared would cancel, and one of the sines will cancel the sign here, so that'd be sine alpha over, well, cos alpha, wouldn't it? Is equal to 196 over 588. That'd be a third. So therefore, well, we could either say sine, uh, so therefore we could say tan alpha as a third, but then if we arctangent of a third, you get a nasty decimal, so that's not really what we want here. I guess what we could then say, 3 sine alpha then is cos alpha. Why is that useful more than tan? Well, but then I can substitute cos or sine into one of these, okay, to simplify it. Because tan alpha is going to be a bit of a mess. But then what I notice is actually this is already sine squared. I think I could be cheeky here. And if I can get this other equation to look like u squared cos squared, or some form of that, I think I can apply the Pythagorean identity, cos squared and sine squared is 1. Um, and that's what I can do here, because then u squared sine alpha cos alpha, that if we then we'll want it to be cos squared, right? Because the other one's sine squared. So then I say 3 sine alpha is cos alpha, therefore sine alpha is a third of cos alpha. So that's going to be u squared of a third cos alpha. Cos alpha is 196, was it? No, 588. There we go. I was say that would have worked. But yeah, that's 588. Cool. Well, then u squared, and then cos alpha times cos alpha is cos squared alpha, and then I'm going to divide by 3 to get rid of the fraction. So 588 times 3 will get me 1764, and then I'm going to call this equation 3. Because then what I notice, equation 1, the u squared sine squared, if I then add them, if I add 1 on this, I get u squared sine squared alpha, add u squared cos squared alpha, is going to be 1764, add, what was it, 1, what was equation 1? It equals 196, okay. Okay, then I can factor a u squared out, and this is where I can see it working together nicely. So then sine squared of cos squared is this summation at 1960. Well, this goes to 1. So therefore, simply u squared is now 1960, which can now solve for u. Is that what they wanted? Yes, it is. There we are. Nice. Okay. Cool. It doesn't look like we need to use u after that. It feels a bit pointless. Uh, we don't need to do anything else with the model now. But yeah, that's the sort of the strategy. If you get an equation like this, that's not the nicest simultaneous equations. It's probably a good strategy to eliminate the alpha, the angles, by using sine squared and cos squared, because that will go to 1. Um, but yeah, there we are. In a refinement to the model, the effect of air resistance is included. The motion of the ball from A to B is now modelled as that of a particle with initial speed v. So all we change, the refined model is used to calculate a value for v, just like we did here with u squared. A state which is greater u or v. So what's the only thing they've changed is u to v. Now everything else with the model it is exactly the same. So it still reaches the same maximum vertical height at 10 at P, and it still reaches B at 120 meters horizontally. Everything else is the same apart from V. But in this new model, it's been slowed down by air resistance. But it's been slowed down by air resistance, but we still expect it to reach the same points, same vertical, and the same endpoint. So what we have to do is to oppose the ball being slowed down and still making it reaches the same sort of points. We're going to have to increase the speed, aren't we, of V? V is going to have to be greater than U to give a bigger starting speed. So then to compensate for it slowing down in the air. So then it still slows down, but it still then reaches the same points. Does that make any sense? Because we're still obeying the model, okay? Because it still reaches 10 vertically at P, and still reaches 120 at B, but we need to increase the initial speed of V to make sure we still have it still reaches those side points at the same period of time, okay, to compensate for the slowing down. So that would be a reason to say that, well, V would be greater because of that. I'm going to write it up here actually. So part C, V would be greater than U because we would need the initial speed to be greater to compensate for the ball slowing down in the air, uh, and still ensure the ball reaches the same points in the model, right? So the points P and B at the same period of time, at the same distance, and everything like that. Everything else is the same in the model. So that makes sense. But yeah, and then part D, give one further refinement to make it more realistic. This is fairly common. So this is stuff like when we said we use G 9.8. So the easy answer is saying use a more accurate value of G, because G is actually kind of like E and pi. It goes on. G is like 0.81. Da, 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 da. It's not just 9.8. So yeah. If we can use a more accurate value G, we can include variable acceleration instead. That's another classic one. Because obviously G is minus acceleration G, pretty much. That's a constant. But realistically, you'll be accelerating variably, because of stuff like air resistance and so on. Variable acceleration. And those are the two I can think of. Those should work pretty much all the time with this sort of question. Um, but let me look at the mark scheme to look at more answers that they might ask for. So I can't find my phone. Oh, there it is. Okay. Also the ball modelled as a particle, which so make sure the ball, so ball, make ball not a particle essentially, not models as a particle. What that means is stuff like the shape and the dimensions, because the ball particle is like a single point essentially. Doesn't have a dimension, but if you start including, it can go left or right, or even in 3 dimensions. It really just changes the model, which is realistic because obviously a ball would be like 3D, right? Um, you can't have 0 dimension or something. No, it's, I don't know. So include dimensions essentially. And also that would mean the mass as well potentially wouldn't be centered, because the particle, the mass is all centered at that point, that single point, whereas the mass might vary among the ball in reality. I don't know, something like that. There's loads of different things. Let me check the marks see if for any more stuff. Um, um, Wind effects. That's interesting. Isn't that just air resistance though? The more accurate value, G, the spin of the ball. I'm not glad I don't know what that means. Size of the ball, again, not the dimensions. The shape of the ball potentially. It might not be, I don't know, completely spherical. I don't know. Not a particle, variable resistance, acceleration, sorry. Surface area of the ball. Okay, so that might affect the air resistance, stuff like that. That affects it. Humidity. Interesting. Okay. Someone please explain that one to me. Okay, humidity. Allow wind resistance and rotational wind resistance. That's the sort of wind they're looking for. Obviously, if you mention air resistance specifically, you want to get the mark, and also anything about mass or weight, as well. They wouldn't allow that either. Um, and I think the reason for that is because we didn't even use the mass in the model, so I don't think I don't know. I don't know. But yeah, those were sort of reasons. So I would learn some of them, even the stuff I write down maybe, because they do love to ask that as a spot question. What is a limitation or excluded air resistance? What is another limitation? You can't just always use the air resistance, sadly. So it's good to have a few backup limitations in your pocket. But yeah, there we are. I think that's all to say, really. Yeah, I'm gonna leave it there. But like I said, with mechanics, I think the best way we can just practice like more than anything because the thing is for exams and in the textbook there's only certain amount of situations they can ask you about, particularly with projectile motion and like force diagrams. It'd be the same sort of situations with forces on a plane or on a rod or whatever every single time. So if you know how to resolve them by practicing, it'd be good for the exam. Same with projectile motion, you always resolve vertically, so that horizontally you're going to use distance, speed, time because it's a constant speed. And you do the same sort of force simultaneous equation, write the same equations of motion. You do that, your force equations, moments potentially. The same stuff every single time. So if you do practice this, you will be setting yourself up well for tomorrow. But yeah, I'm going to leave that there then.